In this video, we will be conducting a linear regression t-test. The paired data below consist of weights in pounds of recyclables, defined as plastics, aluminum, glass, and paper products, discarded by a sample of households over the course of 1 week, along with the size of the households. Is there evidence of a significant linear correlation? First, we will identify the null and alternate hypotheses for a linear regression t-test. We state the null hypothesis, H null, as Greek letter rho equal to 0. This is the statement of no significant correlation between the variables. Our alternate hypothesis, H sub A, can be written as rho is not equal to 0, stating that a significant correlation between the groups exists. In order to determine whether or not we have sufficient evidence to determine whether a correlation exists, we will be conducting a linear regression t-test using a graphing calculator. However, first, we will construct a scatter plot of the regression model and graph the linear function which represents the line of best fit through the data. We will use the following commands to construct our scatter plot and graph the linear function of the regression line. Stat edit, enter the recyclables data into L1, enter household size data into L2, press second, stat plot, set plot to on. Select scatter plot, then press zoom 9, which displays the scatter plot. Next, press Stat, Calc, option 4 for linear regression ax+b. To obtain the results, if you're using an older model, TI-83 or 84, you simply press enter twice. If you're using a newer model TI-84 graphing calculator, you will scroll down to the bottom and press calculate. Once you obtain your results for A and B, you will press the Y equals button, then type in your function. You should have gotten 0.429x plus 0.762, rounding those values for A and B to 3 decimal places. Here, a look at our scatter plot shows a positive and moderate to possibly strong correlation between the variables. It appears that we might have a trend showing that as household size increases, the number of pounds of recyclables discarded also increases. Next, we'll determine the strength of the correlation for our sample data and compare with critical values of the Pearson correlation coefficient, R, to determine whether or not a significant linear correlation exists. The sample correlation coefficient, R, can be found by a process we have already become acquainted with. Stat Calc, option 4, linear regression ax+b on your TI-83 or TI-84 graphing calculator. Note our value of R at the bottom of the display window can be rounded to about 0.834. This indicates a moderately strong, positive linear correlation between our variables. However, we wish to determine whether this correlation is significant. To do so, we must analyze a table of the critical values for the Pearson correlation coefficient R. If the absolute value of our correlation coefficient of the sample, 0.834, exceeds our critical value, then we must reject the null hypothesis and may conclude that a significant linear correlation exists. But how do we determine this critical value? First, we need to determine the degrees of freedom for our sample. Recall that we had 7 coordinate pairs for our data. Our degrees of freedom is found by taking our sample size n minus 2. Our degrees of freedom for our sample, therefore, will be 7 minus 2, or 5. Next, we need to identify our alpha level, which is the threshold of significance that we'll be using for our t-test. Since our alpha level was not stated in the original problem, our default will be alpha 0.05. We now have the information we need to identify the critical value. Degrees of freedom 5 and alpha of 0.05 gives us a critical value of 0.878. Interestingly, although it seems logical that larger households might discard more recyclables, we don't have conclusive evidence of a significant linear correlation between the number of pounds of recyclables discarded each week and household size. This is because our sample correlation coefficient R, 0.834, is less than our critical value of 0.878. We state our conclusion as follows. Fail to reject the null hypothesis at alpha of 0.05. Our sample evidence suggests that there may not be a significant linear correlation between the number of pounds of recyclables discarded each week and household size. As I stated earlier in the video, we can use a graphing calculator to conduct our hypothesis test, and this may be done as a substitute for using the table on the previous page. We do the following. Stat tests, option F, linear regression t-test. Using this option will produce a window similar to the display you see here. Linear regression t-test with X list containing L1, our Y list should contain L2, and we should have a frequency of 1. These are the defaults in your calculator. Next, we'll select a two-tailed test by highlighting and pressing enter over the not equals 0. Finally, we'll calculate. A look at our results shows a p-value of 0.0195 and so on. We could round this to 0.02 if we like. And recall that we are using an alpha of 5% to determine whether or not our results are significant. When using any sort of t-test and comparing p-values, if the p-value is less than alpha, then we reject our null hypothesis, and in this case, here we have our plot twist. Using a linear regression t-test, our p-value of 0.02 is less than our alpha of 0.05, and that suggests that there is a significant linear correlation between our two variables. This appears to contradict our previous result, which showed that we should fail to reject the null. Formally, we might say, reject the null hypothesis at alpha equals 0.05. The sample evidence suggests a linear correlation exists between the number of pounds of recyclables discarded each week and household size. Was our first test result incorrect? Is this result incorrect? The answer here is that neither result is necessarily right or wrong. Conducting our hypothesis test using the critical values for the Pearson correlation coefficient is not the same as conducting the linear regression t-test, which is measuring a difference in the averages or means of our data. We would like our two techniques to yield similar conclusions, and it is often the case that they will. However, when we receive seemingly contradictory results using different methods, it suggests that further study and analysis is needed. This concludes our example. I hope you found it helpful, and we'll see you next time.